A very good morning to everyone. First, let me introduce my group. I am from Group 1 and my name is Loke. I have four group mates which are Muhamad Hamizan Akmal, Muhammad Syafiq, Muhammad Zarul Izzat, and Sofia Aqillah. Now, let me start by giving some introduction about this project. The inverse definite minimum time relay is an overcurrent relay and was developed to overcome the shortcoming of the definite time overcurrent relays. Inverse time is a natural character of an induction type rotating device. If the input current to the device is larger, the faster the speed of rotation of the rotating part of the device. In other words, time of operation inversely varies with input current. Because of this natural characteristic of electromechanical induction this relay is very suitable for overcurrent protection. The current setting of the relay is the pickup value of current that can be adjusted to the required level in the relays. It is achieved by use of tapping on the relay coil, which are brought out to a plug bridge. The tap values are expressed in terms of percentage full load rating of current transformer with which relay is associated. The plug setting multiplier is the ratio between the actual fault current in the relay operating coil to pickup current. The PSM indicates the severity of the fault. The time setting multiplier, which is also called time dial setting, is an adjusting or set up the tripping mechanism of the relay. The dial is a rotating disc, which rotates when fault current in the relay coil reach the pickup current. There is 6 objectives in this project. The first is run load flow of the given power system network to determine the maximum load current at each feeder. The second one is run the short circuit analysis of the given power network system to determine fault current at all buses. The third is the CT ratio is selected and select the suitable accuracy limit current. The fourth is the value pickup setting and time dial setting of all relays are determined. 5 is produce the time current coordination curve of the relays on the system. 6 is to ensure the sequence of the relay operation of the relays for 3-phase short at each bus was correct.
So, we already been given a network by our lecturer. So this is network 1, and we have keyed in the value for group 1 for bus 1 voltage, bus 2 voltage, and so on into this network. So we need to do several analysis, which is for the first part, we need to run load flow to determine the maximum current at each feeder or relay. So to run the load flow analysis, we need to click here and click here. Load flow analysis is so important to ensure that each component runs at optimum operating point. So as we can see here, the value here, ampere in ampere, go through the relay. So for relay 1, the maximum current will be 62.2 ampere. Same goes to relay 2, and relay 3 will be having maximum current 746.5 ampere, and so on. We already tabulate our data here. So here, for each feeder or relay, the maximum load current is here. Okay, for the second part of this analysis, we need to run the short circuit analysis to determine fault current at all buses. So to run the short circuit analysis, we need to click this, and we need to run for the first bus 1 having fault. So here, fault, and we click run 3-phase deviceability. Short circuit provide means to keep the grid safe and good operating. So here, as we can see, when bus 1 having fault, so the fault current through bus 1 is 1.396 kilo ampere. So for bus 2 having fault, current is 16.175 kilo ampere through along the bus 2 component. So for bus 3, we'll be having fault current of 16.175 kilo ampere also. For bus 4, at 10 kilovolt, we can have 15.824 kilo ampere. And for the last bus that having fault, the fault current occur at bus 5 is equal to 15.536 kilo ampere.
So for part C is transformation ratios of the cities were selected. Then class 5 PCT with accuracy limit factor equal to 5 and suitable accuracy limit current were utilized. So during overcurrent grading process, the current transformer accuracy must be maintained to a certain level. This is possible with the burden expressed in VA at the rated current, and the wiring should be reasonably low. When we put a fault at bus 1, we can see that at relay 1 and relay 2, the maximum current is 62.2 kilo ampere. When the fault is present at bus 1, the fault current at relay 1 and 2 is 0.272 kilo ampere. So the CT ratio we got is 100/1, which is based on the maximum current. And then we calculate for the accuracy limit factor, which is the fault current at relay 1 and 2 divided by the CT ratio, and then we got 2.72. So here is the, we choose 5 because it was the nearest for the accuracy limit factor. And then for accuracy limit current, we just multiply the accuracy limit factor times rated current, which is 5 ampere. And then we got the class which is 5P5. This is the setting for the relay 1 and 2, 100/1. Then the design class designation is 5P5, and the burden is 2.5 VA, same as the relay 2. And then for the relay 3 and relay 4, the fault current at relay 3 and 4 is 3.265 kilo ampere, and then the CT ratio is 800/1. And then we calculate for the accuracy limit factor, which is 4.08, and then we take 5. Then we calculate the accuracy limit current, then we got 5A. Then the class designation is 5P5. Okay, and the setting is here. And we put the CT ratio 800/1, and the class designation 5P5, then burden 2.5, same as this CT ratio 4. And then when we put at the when we put fault at bus 2, we can see relay 5, the fault current at relay 5 is 7.456 kilo ampere, and then the CT ratio we put as 400/1. Then we calculate for the alternate accuracy limit factor, which is 18.64, nearest to 20, and accuracy limit current we got 20 ampere. Then the class designation we got 5P20. This is the setting for the CT ratio, the class, and the burden. And for the relay 6 and 8, we take the fault current at relay 6 and 8 is 5.867. Then the CT ratio is 900. and we calculate the accuracy limit factor, which is 5.41, and the nearest is 10. And then the accuracy limit current is 10 ampere. The class is 5p10. So at 6 and 8, setting the ratio is 900/1. The class is 5p10, same as the relay 8. 900/1, 5p10. Then for the at bus 3, when we put the for at bus 3, the fault current at relay 7 and 9 is 3.595 kA. And then we calculate for the accuracy limit factor, which is 5.14, and then the nearest is 10. Then we calculate for the accuracy limit current is 10 ampere, and then class is 5p10. So here is the setting. And primary is 700, and this is the T ratio 7/1, and the class is 5p10, same as the relay 9. And then for the next is for at bus 4, which is at relay 10. The for relay 10 is 0.433 kA. Then the safety ratio is 100/1. Then we calculate for the accuracy limit factor, and then we got nearest to 5 and accuracy limit current, which is 5 ampere. So we setting. Okay, this is safety ratio, and then class designation. For the relay at relay 11, the current at relay 11 is 4.503. Then the accuracy limit factor is nearest to 5, and accuracy limit current is 5 ampere. Then the class designation is 5p5. So this is the setting for the relay 11. And then when for at bus 5, we can see that the fault current at relay 12 is 3.002 kA. Then accuracy limit factor is nearest to 5, and accuracy limit current is 5 ampere. Then the class is 5p5. And for the relay 13, we can see that the fault current at relay 13 is 0.647 ampere, and accuracy limit factor calculate, we got 4.31, nearest to 5, and accuracy limit current is 5a, and the class designation is 5p5. So this is the setting for the relay 12. This is the ratio, then the class designation. And for the last relay, this is relay 13, this is the ratio, class designation.
For part D, we need to determine the values of pickup setting and time level setting. The formula of time level setting is maximum load current over CT ratio multiplied by 100. And the formula of time level setting is relay operating time over relay characteristic operating time. These are the calculations of pickup setting and time level setting for all relays. So this is the table of the results of pickup setting and timer setting that we have calculated. This result will be used for the simulation. For the simulation, to key in the data of pickup setting and timer setting, we need to double click the relay, go to the OCR section. After that, insert the calculated value of pickup setting into the pickup section, and insert the calculated value of time dial setting into the time dial section. This method is applied to all relays with its respective pickup and time dial values. And that's all for part B.
Okay, so for part E, time current coordination curve of the relays on the system was produced. So here we talk about how the time current coordination curve of the relay. So the graph here it shows for relay 1 until relay 5. So from this figure, we can see that the relay 5 operate first, then followed by the relay 4, relay 3, 1, and the last is relay 2. The sensitivity of the relays increases from load to source. The system for relay 1 until relay 5 is well coordinated because there was a good discrimination as the curve of the relay do not overlap each other. Relay 1 and relay 2 look like overlap because they are in parallel, same as relay 4 and relay 5. Okay, so next, this figure shows for the relay 6 until relay 9. So from this figure, we can see that the relay 9 operate first, and then followed by the relay 7, and then relay 8 and relay 6. The sensitivity of the relays increases from load to source. The system for relay 6 until relay 9 is well coordinated because there was a good discrimination as the curve of the relays do not overlap with each other. So relay 7 and relay 8 and relay 7 and relay 9 look like overlap because they are in parallel, same as relay 6 and relay 8. After that, this figure is show about the time current coordination for relay 10 and relay 13. From this figure, so we can see that the relay 10 operates first, and then followed by the relay 13, and then relay 12, and last is relay 11. So the system for the relay 10 until relay 13 is coordinated well because there was a good discrimination as the curve of the relay do not overlap with each other. So yeah, that's all for the part E.
Now, I will explain about the sequence of relay operation of the relays for 3-phase short at each bus. This is the example of the 3-phase short occur at the bus 1. And this is the sequence of relay operation. So the data was collected and put in this table. When the fault occur at the bus 1, the relay 7 and relay 9 will operate first, then followed by the relay 8 and relay 6 and others relay. And when the fault occur at the bus 2, the relay 5 will operate first, then followed by others relays, same as the fault occur at the bus 3. The relay 5 will also operate first, then followed by the relay 7, relay 9 and others relay. When the fault occur at the bus 4, the relay 6 and relay 8 will operate first, then followed by the relay 5 and others relay. And when the fault occur at the bus 5, the relay 7 and relay 9 will operate first, then followed by the others relay. So, the conclusion of this project is the simulation result of load flow and short circuit analysis, the section of the transformation ratio of the city with justification, PU setting with justification, time delay setting with justification, times current coordination curve, and the correct sequence of the operation of fault at each bus was tabulated. The 3-phase symmetrical fault occurring at each bus was determined to obtain the relay ROT nearest to the fault bus. The backup relay was operated if the closed relay to the fault bus failed to operate. It was necessary to set the delay time interval because when there was a fault occur, the backup relay would be able to withstand certain amount of large fault current before its next operating time was reached and tripped. The purpose was to prevent the relays tripped simultaneously, as the whole system would be shut down easily every time the fault occurred. The regular maintenance has to be done manually on the current transformer, relay, and circuit breaker, so they are always in good condition to operate whatever fault occurs in the power line system. That's all from group 1. Thank you.